I was asked to essentially describe you, tell you about the black holes. I mean about some strange properties of black holes. I don't know the level of people here, so I will start from almost very beginning. Not very beginning, because I will start from non-inertial reference systems, and then I'll continue with black holes. Okay. First, I will describe to you somewhat similar phenomenon to black holes, the phenomenon of homogeneous accelerative motion in flat space. So the flat space metric is just Minkowskian metric. Actually, I probably use a different signature, right? I use the signature of Landau-Lifshitz there. So I put the speed of light to 1. So this is Minkowskian metric. And I want to consider the homogeneous accelerative motion in this reference system. Homogeneous accelerative motion is described by the following world line. It's 4-vector. It's 1 over a sinh. It's a hyperbolic sign of as. 1 over a hyperbolic cosine of as 0, 0. So I consider accelerative motion along the first axis, and it's very easy to check that z dot squared is minus a squared, where z dot is just dz over ds. S is a proper time. So this equation tells us that we have a constant 4 acceleration. Constant 4 acceleration. 4-vector of acceleration is constant. It's space-like. Okay, it doesn't matter that it's space-like, but it is space-like. Okay, now if you consider this is a relativistic accelerative motion, but you can see that for slow velocities, for small velocities, it reduces to the standard accelerative motion. So if the velocity is very small in comparison with the speed of light, you just get the standard textbook, high school textbook accelerative motion. But if if the speed increases, the curve is a bit different than what would you expect. So it's actually very easy to check that this is actually z0 squared. That is z0. This is z1, z2, z3. z0 squared minus z1 squared is just minus 1 over a squared. Very easy exercise, following from the fact that cosinus squared minus sinus squared of whatever argument is just 1. This is equation of hyperbola. Hyperbola. So we have the following hyperbolic motion. That's the reason it's called hyperbolic motion. Let me erase something. So if I draw space-time like this, so if I on the plane x0, x1 will draw this curve, it will be hyperbola. Like this. So now I want to make coordinate change. You know that if I make coordinate Lorentz boosts, this metric doesn't change. But I want to change now to curvilinear coordinates. Curvilinear in the sense, we will see that it will be curvilinear, but I want to change to the reference system in which this guys which accelerate with which perform such a motion are static. how it goes. They don't change their spatial position. Okay, so you see, how do we observe the reference systems? Reference systems we observe in the following sense. For example, if you consider just Cartesian coordinates as follows, right? The lines of constant x coordinate are like this, and the lines of constant x0 coordinate are like this. And it's actually very easy to understand what are these lines. These lines are nothing but world lines of particles which are static in the space. You see? So I want to draw a coordinate system which is static in this. So these are the lines of the accelerating observers. Changing A, I change this curve. They, how you call it? They becoming closer and closer to the asymptotes of this hyperbola when A is increasing. When A is increasing. So I want to draw, write a metric which describes such a coordinate system. I didn't yet draw for you constant timelines as here. These are constant timelines. The analog of constant timelines here will be like this. I will show you in a minute. So, what is the coordinate change I'm going to perform? I want to transfer to the following coordinates. I want to use t, represent t as rho times sinh of tau. This is dimensionless time. It's not a proper time. It doesn't coincide with the proper time. And x1 is rho cosinus tau. This coordinate change is inspired by the form of the world line. Now, if I use this and then perform d rho plus rho cosinus tau d tau, and the same do here, and then square it and put it into here, and use the fact that cosinus squared minus sinus squared is equal to 1, I get that this ds becomes just of the following form. It's just rho squared d tau squared minus d rho squared minus dy squared dz squared. Just in case. Sometimes I will be using x1, x2, x3, and sometimes I will use x, y, 0. I hope it won't cause confusion. So my coordinate system, Cartesian coordinate system, is changed into, this is called Rindler coordinates in the literature. Rindler coordinates. It's curvilinear because here the metric is constant. It's just 1, 1, 1. Metric, the matrix of the metric tensor is just 1, 1, 1. 1 minus 1 minus 1 minus 1. But here it's coordinate dependent. It's rho squared minus 1 minus 1. So this is curvilinear metric. Now, the physics in this metric is very interesting. And it comes from some of its properties. Let us discuss in a second. You see, I draw for you, from this coordinate change, rho sinus tau and x rho cosinus tau, you immediately can see that x squared minus t squared is just rho squared. So the constant rho lines are hyperbolas. This is constant rho lines, as I promised you. So we get hyperbolas as one of the lines of the coordinate system. And then if I divide t to x, I get hyperbolic tangents of tau, or cotangents. I don't remember who is tangents, what is tangents and what is cotangents. Anyway, so constant tau lines are exactly straight lines, like this, as I promised. And now let us observe several interesting things of this situation. You see, this world line, which I wrote to you, z of s, which is 1 over a sinus as, 1 over a cosinus as, 0, 0. It is eternal accelerative motion. So this is a world line which is describing motion when you always accelerate with a, from minus infinity to plus infinity. This is impossible, physically impossible motion, but we are idealizing the situation. So we are assuming as if this motion is possible. Meanwhile, this coordinate change is, of course, possible coordinate change. I can make any coordinate change I want. I do that on the Euclidean plane. I can do that on in Minkowski. This is part of my entire Minkowski spacetime. So if I have such a motion, I can describe it as follows. Here, at minus infinity, my particle has speed of light. So the speed is just tangential to this curve, right? So when at minus infinity, the hyperbola approaches its asymptote, so the tangential to the hyperbola is just a 45 degrees angle with respect to x0, which corresponds to the motion with the speed of light. Then my particle decelerates. Here it stops, and then continues to accelerate, and reaching the speed of light again. So acceleration is always in this direction, meaning that here it slows down, then accelerates. So now it has an interesting property. It has an interesting property. If somebody from here, from behind, will start to radiate light to catch up with this particle, which performs this motion, this light will never cross this hyperbola, meaning that light will never catch up with such a particle. You see? This particle will always escape from the light if it will eternally accelerate. So you have to radiate some distance away from the particle. This distance is just 1 over a. If I restore the speed of light, it will be c squared divided a. So if I radiate towards eternally accelerating particle light ray from such a distance, this light ray will never catch up. That's the reason these asymptotes of the hyperbolas are horizon. It's event horizon for the eternally accelerating observers. That's what makes this picture very similar to the black hole. So event horizon in the following sense. From this region, you can this particle will never receive any signal. Meanwhile, to this region, it cannot send signals. You see? If a particle emits a signal from here, it goes in that direction, but never into here. Okay, this horizon appears in this metric as ρ equals to 0. That's a place where this metric degenerates. And ρ equals to 0 corresponds not to a point, but to x squared equal to t squared, which can be solved x equal to plus minus t, which are these two lines, this line and this line. You see? Okay, that's a horizon, event horizon of this observer. Now I am transferring to black holes. I think I said, Actually, by the way, I feel myself way better if I'm interrupted with questions. If I'm not interrupted with questions.
And your horizon coincide with the light cone?
Sorry?
Your horizon coincide with the light cone here?
Yeah. Horizon is always coincided with the light cone. It's a property of the horizon. It's a curved, in general situation, is curved light cone. The question is, what is the name of this guy, of this 4 vector? 1 over A. It's a 4 vector of the position of the particle at the moment it's of its sinus. It's at the moment S. At the moment S, it's positioned at this 4 vector. So it's a 4 vector of the position of the particle at the moment S. Okay, you can have this name. So there.
I have a question. You described the situation about any other observer who cannot detect this accelerated guy. So how the situation with these horizons looks like from the perspective of accelerated observer? I mean, if we move with this guy with constant acceleration.
I don't understand the question. Again, repeat.
Mean, these horizons are for observers. I mean, for laboratory observers.
No. This horizon is for. No. Laboratory observer. Okay. Let me. It's good that you ask questions now. Now I can feel what you understood and what you didn't understand. This horizon is a property of the accelerative observer. It is horizon for the accelerative observer. It has nothing to do with the laboratory observer. If laboratory observer is some inertial guy, so we have, I'm drawing 2-dimensional part of this entire 4-dimensional Minkowski spacetime. So inertial observer is just standing or moving with constant velocity. You see? It doesn't have any horizon, this guy. It observes all spacetime. It can send signals to any part of the spacetime and receive signals from any part of the spacetime. Meanwhile, accelerative observer moves along this very peculiar curve and cannot receive signals from here just because light rays are just 45-degree angle. So they cannot catch up with this guy. Only from here you can receive signals. And to this region you cannot send signals because signals are propagating at speed of light or slower. And so you cannot send signal to this region.
So it is concerned about...
It's a property of the accelerative observer. Exactly. And the property follows from the fact that this curve has peculiar features. So this event horizon, it's a property not of the space-time, it's a property of the peculiar motion.
So the space that this observer is measuring is another space. It's not like
No, it's the same space. You see there is inequality here. Yeah. This is equal to this one. I didn't change anything. I just draw different coordinate system in the same space-time. You actually know, for example, recall what we learned at school. This is Cartesian 2-dimensional coordinates. Cartesian 2-dimensional coordinates have these lines of constant x and y. Now you can change to polar coordinates, r squared d phi squared plus dr squared, which you can achieve by doing r cosine phi and y is equal r sine phi. So this coordinate system is like this. These are lines of constant phi, and these are lines of constant r. But this is the same plane. I draw different coordinate systems on the same plane. Actually, notice this coordinate change is not much simpler or not much harder than the one I made to transfer from this to this. Actually, they are very similar. Instead of cosine and sine, I just used cosinus and sinus.
But in the relativistic case, we cannot cover the whole space.
Yeah, we cannot cover the whole space. That is because, you see, that's actually interesting to stress. Because in this coordinate change, rho sinh of tau, x rho cosinus of tau, you can very easily see that for rho greater than 0, and I also always consider rho greater than 0, I will discuss in a moment rho negative. For rho greater than 0, x is always greater than t. You see? Always. Actually, even modulus of t. And that's the reason it covers right quadrant. If I use rho negative, I will cover the left quadrant, but never entire space-time because of this coordinate change. So it happens in space-time that some coordinate changes do not cover entire space-time. Actually, in space, you also can invent coordinate changes which will not cover entire space. It happens that coordinate systems do not cover, for example, it's very easy, down to Earth, meridians and parallels, they cover Earth. This is coordinate system we use on Earth. But imagine there is a hole in the Earth. I don't know, как пещера, cave in Earth. What coordinate system will you use to describe a position inside the cave on the wall of the cave? You cannot use meridian and parallel. So your meridian and parallel cover only part of this space, which is the surface of Earth with cave. And one more thing I wanted to say. It's good that you asked because I almost forgot to tell you about this story that it doesn't cover entire space-time. So let me write back some of the dt squared minus dx squared, and I transfer to rho squared d tau squared minus d rho squared plus minus dy squared minus dz squared. First of all, why do I like this coordinate system? Well, on top of the fact that constant rho lines describe for me world lines of accelerative observers. So in this coordinate system, accelerative observers are static. Second thing is this coordinate system is static in the sense that it doesn't change under time translations and doesn't change under time reversal. And eternal accelerative motion actually has this property because when you eternally accelerate along this line, nothing changes. Physics at this position and at this position is the same. Moving along this line, you will not distinguish two different positions in the following sense, because this hyperbola is very easy to check, is an orbit of the Lorentz group. So if you perform Lorentz boost, it doesn't change. So Lorentz boost is just the following transformation. It's t equals t prime is equal t cosinus theta plus x sinus theta, and x prime is t sinus theta plus x cosinus theta, So if you perform such a transformation, your world line is just shifted. So this, instead of becoming 1 over a sinh a tau, it's just shifted. 1 over a cosinus a tau. It's a very easy exercise to check. So performing Lorentz boost just moves you along this line, changes your speed, but doesn't change the fact that acceleration remains the same. So that's the reason I like this coordinate system, because it describes the fact that the motion with eternal acceleration is homogeneous motion. The metric is homogeneous. Okay, and one last thing I wanted to stress. Real motion would be motion as follows. You move with some speed, then accelerate for a while, then continue moving with gain speed. You see? So your world line coincides with hyperbola only partly. I'm not a very good painter, I'm sorry. Just let me draw it on this picture. I want to stress one point. So these are asymptotes of the hyperbola. So suppose you were static until some moment of t equals to 0. Then you accelerated for a while, and then you continued your motion with constant gain velocity. So then you don't have a horizon, because this here you essentially continue moving along the tangential to the hyperbola, and tangential to the hyperbola only asymptotically approaches 45 degrees. So it's always less than 45 degrees. Then any light emitted from behind will catch up with you. No horizon. Okay? So that's it. That's the last thing I wanted to stress about this point. Now I am transferring to another subject. So I will describe to you Penrose diagrams, because they are important to describe properties of the black holes. Or not only of the black holes, but also of other space-times. Very convenient tool, Penrose diagrams. So the idea behind Penrose diagrams is very simple. You actually, if you had a good school, you actually had it at high school. At least I had in my high school times. It's actually stereographic projection, nothing more than the stereographic projection. Stereographic projection is the following thing. It's a projection from the plane to a sphere. There are two ways to do that. You either project like this, or you project like this. Either the sphere is cutted by the plane by half, or just standing on the plane. The stereographic projection is a map between points on the sphere, and points on the plane. Map is as follows. You take the pole of the sphere, you draw a straight line which intersects the sphere. So it intersects the sphere at one point and intersects the plane at one point. And the map is between these 2 points. So every point on the sphere is mapped to a point on the plane. You can check that if you draw lines on the plane, they correspond to circles on the sphere, actually big circles. And moreover, you can check that 2 lines intersecting at the same angle correspond to 2 circles intersecting at the same angle. So this map respects angles. It's conformal map. Conformal map. I don't remember which one of those corresponds to the conformal map that I'm going to do. The conformal map is the following thing. You essentially map dz bar 1 over 2 dz bar. So this is non-compact space, plane, and this is compact space, sphere. So the idea of this stereographic projection is that you map plane on compact space. So the idea behind Penrose diagram is also to map your space-time to a compact region where you can understand all the causal properties of the space-time from the scratch, immediately see them, the causal properties. So now I will do, and one last thing I wanted to stress, that the eternity of the plane, the infinity of the plane, is mapped to a single point. So the pole corresponds to any point at infinity. Now I do perform the following transformation with this. The idea is the following, that you single out from your space-time its two-dimensional part, which is relevant for physics and contains time, and do the map. Here you just take, say, t and x, and perform the following transformation. Tangents psi plus minus xi over 2. And psi and xi are changing from minus p to p. Meanwhile, t and x are transforming from minus infinity to plus infinity. So when they approach, when the argument of the tangents approach pi over 2, it goes to infinity. You see? This way you cover entire range of the coordinates of original spacetime. If you perform such a transformation, your metric transformed into 1 over 2 cosine psi plus xi over 2, cosine psi minus xi over 2, and here is just d psi squared minus d xi squared. Again, no questions? Everybody understand?
The question is about the last. So you have here a four-dimensional metric, and after the final,
Yeah. I do not touch the other two coordinates. So I just single out this part, two-dimensional part. As I told you, I have to single out from four-dimensional space-time relevant for physics two-dimensional part and perform the transformation. So you see this, if I erase this and erase this, you see these guys are running from minus infinity and to plus infinity. Meanwhile, this space is compact. If I drop the conformal factor, I do not, how you call it, I make a conformal transformation. Let me just stress it a bit more. So I essentially, originally I had this space, and now I transform it to psi and xi space. So I entirely, if I draw now these guys, these coordinates, they range from minus pi to pi. So from minus pi to pi, from minus pi to pi. So the entire plane is shrunken to this square by the conformal map, if I drop the conformal factor. The conformal factor actually does the job, because when the argument of the conformal factor approaches pi over 2, cosine becomes 0, and conformal factor blows up. So essentially, by dropping it, you shrink your infinite plane onto the square. Because at these boundaries, the conformal factor blows up, goes to infinity. Okay. Now, what happened? So I mapped my plane to the compact space, but it is not a sphere. It's just because I did that with this, because of this signature is present here. Remember that under the standard spherographic projection, all the infinity of the plane gone into one point, pole of the sphere. Here, the situation is a bit different because different lines have different properties. Namely, it can be then ds squared is greater than 0, ds squared equal to 0, ds squared less than 0, depending on whether you deal with time-like lines, light-like lines, or space-like lines. And that's the reason this thing happens. So these are light-like. Let me just stress one thing. You see, when ds squared is equal to 0, that corresponds to the situation that t is equal to plus minus x. And immediately it also corresponds to psi equal to plus minus psi. So light rays were straight lines at the beginning, before the map. Light rays were straight lines with 45-degree angle with respect to both lines. And here again, light rays are 45-degree straight lines. That has to do with the fact that I did the conformal map. I respect the angles between the lines. So, and now, what is this point? This point is essentially whole line t from minus infinity to plus infinity at x equal to minus infinity. This point is the same line at x equal to plus infinity. So this point is the entire time-like line mapped to a point. This point is space, x running from minus infinity to plus infinity at t equals to minus infinity. And this is the same thing at t equals to plus infinity. Meanwhile, these are light-like lines, light-like lines. This is called light-like past infinity, light-like past infinity. This is light-like future infinity, light-like future infinity. Why is it light-like future and past? Because light rays can propagate either in positive x direction or in negative x direction. This corresponds to this motion and this motion. Light rays originate at these lines and end up at these lines, as this line. Or they can originate from this line, then they end up at this line. So that's the reason this is at past infinity originate here. Light rays originate. At future infinity, they originate here, terminate here. Okay, that clear? Okay, that I described to you spherographic projection of Penrose diagram for Minkowski spacetime. And now let us describe some of the properties of Minkowski spacetime on this diagram. Here is everything trivial. Then I will draw for you Penrose diagram for black holes, and we'll derive the Penrose diagram for the black hole, and understand its properties of the black hole looking at the Penrose diagram. So I draw again this rectangle, actually square. It's a square. Minus pi, pi, minus pi, pi. This is x, this is x0, or t. x0 and t is the same. Okay, now, how can I draw a world line of a regular observer which doesn't accelerate eternally and can move only with speed less than speed of light? So it's some curve which is time-like. Time-like is the following sense. If I take a point of this curve and draw a light cone passing through this point, this curve is always within the light cone, so it cannot go like this. Otherwise, it means that the particle moves with the speed higher than speed of light. So at any point of this curve, it is situated inside the light cone. This here and here, not outside. So as a result, this point, this curve can start from here and end here. It cannot go like this. Otherwise, it will break this rule. You see what I mean? So what about Cauchy surface? Cauchy surface is a space-like surface on which I impose, for example, initial conditions for some differential equations to describe how the system evolves. Cauchy surface does the opposite. It should be space-like, so it should lie outside of the light cone. You see? That's the reason Cauchy surfaces can be like this. So this is entire space at a given moment of time. As I change moment of time, my space is just, these are Cauchy surfaces. I always respect this property that they should lie inside, outside of the light cone. These are Cauchy surfaces. These are not necessary X constant surfaces. Cauchy surfaces can be different ones, but X constant are among these lines, among the lines of this type.
Does these surfaces depend on the motion of
No, it has nothing to do. It's a property of space-time. Yeah, I just X constant lines are just among the lines of this type.
Here X isn't const in diagram.
What do you mean? If you ask me to draw a line X equal to constant in this diagram, it will be line of this type. On this line, X will remain constant. Yeah. Line, sorry. It's T constant lines. Cauchy surface is T constant. X constant, X equal constant, this is T constant lines. Cauchy surfaces, sorry. X constant, it's good that you're asking, you see. X constant lines are like this. This sorry. Now we can see the property of the space-time on this diagram. You see, if you choose on the plane Tx, I draw the, okay, probably, yeah. It's better if I draw like this. And they range from minus pi to pi, from minus pi to pi.
Your previous picture was the same. Change.
What do you mean, the same?
Your previous picture.
I mean, okay, yeah, the same. Nevertheless, if I ask the question X constant, how it looks like, X constant line after the map, this is a line, T constant, this is a line, or vice versa. T constant, X constant, line. So now, an observer performing eternal motion, possible motion, this is a possible motion, it doesn't accelerate eternally. It either static or moves with some finite velocities or accelerates for finite times under action of some forces. This guy will receive signals by this moment of time. This guy will receive signals from this region. You see? I mean, because light rays propagate at speed of light, so you, by this time, from here, you will receive signals. And you can send signals to this region. But as you move this point, you cover entire space-time. You see? Being here, so by this moment, you see this fraction of this Cauchy surface. But as you move towards future infinity, you see entire Cauchy surface. So there are no regions in this space-time which are causally disconnected. In Minkowski space-time, you see everything. Sooner or later, you will see everything. Now, suppose you were static and then started to accelerate for eternity. Your world line will be like this because you will be approaching speed of light. And it will not end up here, but it will end at this light-like infinity because you will be approaching speed of light. And now you will have a horizon. From this region, you will not receive signals. You see? So this property you already see on the Penrose diagram. Now I'm transferring to black holes. So I'm done with flat space-time and curvilinear coordinates. Now I will do the same for the black holes. And describe their properties. The black hole metric looks as follows. I will not be solving Einstein equations. I assume that you know them and can solve. Anyway, it will take another 2 or 3 lectures. Let's not spend time on that. This is famous Schwarzschild metric. RG is the gravitational radius. Essentially, it's a size up to which you can shrink your body, this body, to make it black hole. So for any given mass, you can write RG. I think it's, if I'm not mistaken, it's 2gm divided by c squared. I mean, I don't remember about the c squared. M is the mass, g is Newton's constant, this is speed of light. So for example, for the sun, if sun has a size of order of a million kilometers, it's 700,000 meters, 700,000 kilometers radius of the sun. Huh? Yeah, if you shrink the sun to the size equal to 2.7 kilometers or of order of 3 kilometers, the sun becomes a black hole. So regular size of the sun is 700,000 kilometers. If you shrink it to 3 kilometers, for the Earth it's 9 millimeters, 1 centimeter. For such a mass as the Earth, you should shrink it to 1 centimeter to make black hole.
This lecture,
Omega squared. Yeah. Yeah. It's d omega squared is d theta squared plus sine squared theta d phi squared.
a solid angle.
Yeah, essentially it's a solid angle. It's a metric on unit sphere. Well, solid angle probably you mean the volume form for this metric. Volume form for this metric is sinus theta d phi. So this guy is just square root of this metric times d theta d phi. Square root of the determinant of this metric, which is sine. So this is solid angle. Okay. So the relevant part for physics is this one. I can neglect this part and make Penrose diagram for this space-time. But before doing that, I should be careful. Yeah, one important thing. This guy solves Einstein equation. In this simplest case, without matter, Einstein equation looks like this. This is Ricci tensor. But Riemann tensor for this metric is not equal to 0. It's a curved space-time. Riemann tensor is not 0, but if you, let me write it like this to make it more relative. Sorry? This is Ricci tensor. If you want me to describe it from first principles, it will take another lecture. This is Riemann tensor. You can construct this guy from the Riemann tensor by contracting indices. This and this. So this is essentially mu alpha, nu alpha. Okay, just important thing, because before that I have been describing to you the situation for the flat space. In the flat space case, Riemann tensor is 0. Not only the Ricci tensor is 0, but Riemann tensor is 0. The flat space is flat. Essentially, this tensor, it has very simple physics. This tensor tells you the strengths of the tidal forces. Knowing it, you can say the difference of if you free fall, if you are in a free fall in Earth's gravity, the tensor tells you the difference between the attraction to Earth of your top and bottom. Okay, now I want to describe the physics of this black hole. Before going ahead, let me tell you first several things. How much time do I have? 15 minutes. Okay, that's good. First of all, you see this metric is degenerate when R equals to Rg, it degenerates. But this degeneration is very similar to the degeneration of this metric. Or this metric. You see, this metric is also degenerate is equal to at r equal to 0. The polar coordinates, they degenerate at r equal to 0. Degenerates in the following sense, that phi cannot be defined at r equal to 0. Phi can have any number. You see, all these phi constant lines pass through one point, r equal to 0. That's a point where the metric degenerates. But space-time itself has nothing special at this point. It's flat space-time. Similar to this, it degenerates at rho equals to 0, but nothing special happens at the horizon. Horizon is nothing special. It's just a bended light cone. In this case, it's not even bended. It's just a light cone. Space-time there flat, nothing singular happens, nothing special happens, etc., etc. There is no any mystery in the horizon. Bended light cone, nothing more. Light cone is a trivial thing.
But you should start from the range where R is more than R.
Yeah. That's I'm going up to that. Going up to that point. So here the metric degenerates, but there is nothing special happens at that point for the following reason. If you calculate the Riemann tensor and calculate some invariance from it, like for example square of this Riemann tensor doesn't have any indices, it's invariant. Invariant is something which doesn't transform under the coordinate transformations. And this invariance thing doesn't become infinite at r equals to rg. At r equals to rg, it's less than infinity. So it's finite. Tidal forces do not become huge at that point. Nevertheless, if you extend your space-time behind the horizon that we will discuss in a moment how we will do that. R squared blows up as R goes to 0, to that point, at the point when R goes to 0. But let me stress one thing, that this metric is applicable only for R greater than Rg. I will describe to you how I will extend it behind Rg. Yeah.
Greater or greater than equal?
Sorry?
So you will
Great.
equality.
This metric, it doesn't matter. With physics precision, it doesn't matter. Okay. Now, let me describe to you how I will avoid the complication with this. I will do the following thing. I will extract, so I will do the following transformations with this metric. This is so-called tortoise coordinate. Tortoise coordinate is as follows. It's just dr star squared is equal to dr squared minus 1. So it's a trivial transformation. I can integrate this with choosing some sign and choosing the constant of integration. I get that r star is something like r plus Rg log of R divided by Rg minus 1.
And the t in the left and the right
Is the same. So I change only R coordinate. So you see this is a transcendental equation. To express this function here in terms of R star, I should solve it with respect to R, which is impossible in usual functions because it's a transcendental equation. So one usually assumes that this is a function of R star, which is the solution of this equation with respect to R.
Why the power 2?
Oh, sorry, no power 2. I just extracted. Yeah, power 2 is here. Yeah. Okay. You see, and then this is so-called tortoise coordinate. Tortoise because it's as you approach horizon, as R goes to Rg, R star goes to minus infinity. So your log is approaching closer to 0, and R star is approaching to minus infinity. So you essentially shifted the horizon to minus infinity in terms of this coordinate. That's the reason it's called tortoise. It never approaches the horizon. Okay. But then you can choose the following transformation. It's called Eddington-Finkelstein coordinates. So I make the following coordinate change. From T and R star, I transform to T and V, which is T plus R star. In terms of this coordinate system, I obtain the following. 1 minus Rg divided by R dv squared minus 2 dv dr. I hope it's clear. This is V. And now, this metric is not degenerate at R equals to Rg. Although this vanishes, the metric tensor has the following structure. It's 1, 1, 0, 0. You see? It's not diagonal.
Should there be parentheses?
Huh?
Should there be parentheses on the
No,
side?
no, exactly. That's the point. No parentheses, as it's written there. No parentheses. If there were parentheses, it would be degenerate. It is not degenerate at that point. You see, here, what happened is that some of the, how you call it, eigenvalues of the metric tensor were not eigenvalues. Well, actually, it's eigenvalues, but I shouldn't stress that I'm talking about eigenvalues. It just becomes like, how you call it, some of the elements of the metric is 0, another one is infinity, and essentially, but here nothing like that happens. Just a diagonal term vanishes, but non-diagonal are not vanishing. The metric tensor is not degenerate. Okay. Oh, so when it is not degenerate, I can extend R beyond. Now this metric is applicable from 0 to infinity. So I can extend R from 0 to infinity. And that's how I calculate this Riemann tensor. So this is also this metric plus R squared d omega squared minus, sorry. This four-dimensional metric solves Einstein equations. Solves Einstein equations, solves this equation, and describes the black hole even inside the horizon. Inside the horizon. And that's how I calculate Riemann tensor for any R in this metric, and can calculate its invariance. So you see, this R, although I should probably name it as R prime, because this R prime is not the same R here. They coincide beyond the horizon, but inside horizon, this can be used. This one cannot be used. Actually, I can tell the following thing. I can use the same metric inside the horizon, putting here prime, prime, prime. But then I have to use the fact that R prime is less than RG, and then they essentially flip. R prime plays the role of time, meanwhile T prime plays the role of space, spatial coordinate. And the metric becomes time-dependent metric. Nevertheless, it solves Einstein equations. Okay, I am almost done with, well, this is a good point when I can stop before continuing further, before doing Kruskal coordinates and drawing for you Penrose diagram for the black hole, which will be done at the next lecture. And I will describe properties of black holes at the next lecture. Now I can answer questions. I have like less than 5 minutes left, if there are questions.
Here the horizon is the line of R or not. Is equal RG?
Yeah. Horizon is at R equal to RG. We will see that, actually. We will see that event horizon corresponds to Schwarzschild horizon when R equals to RG. Yeah.
Thank you for interesting lecture. So I have maybe 3 questions for the viewing of our session people. The first one about the stereographic projection. If I correctly understand, I think we have some tension in the South Pole, yes, because we can come to this point by different ways. And
You mean you mean in case of such a projection?
yes.
But you can use this projection, and then you don't have this problem.
We need to combine 2 charts, yes?
Yeah. Well, the lower hemisphere is mapped to the disk, inside the disk. The upper hemisphere is mapped to outside of the disk.
It's clear. So the second one about such metrics. For instance, we get some metric with singularities. How we can understand this singularity? What is the nature of this singularity? These coordinate singularities, such that all these physics singularities without many numbers of coordinate transformations.
Just by calculating invariant. You just calculate invariant. I mean, Riemann tensor squared. If it is finite, this is not a singularity of the space-time.
Can have several singularities.
So what do you mean? Singularity is where this guy is, some invariant is blowing up, becomes infinite. So you calculate this guy as a function of your space-time coordinates. At those points where this guy blows up, you have a singularity.
Okay, I understand. But if we have, for instance, two singularities in our
What do you mean by two singularities? 2 points of singularity. Yes. Singularity can be not a point, but a line. Actually, r equal to 0 is not a point.
Oh, yes.
R equal to 0 is not a line. Is not a point. It's a line. Actually, not even a single line. You will see. It's a surface, yeah.
Maybe the question is, can be this singularity lines can be
Separated,
yeah.
not connected. Yeah, this is the case for this space-time. Looks like you are shocked.
Yes, and the last one, if I correctly understand, we get this solution in the vacuum, but we don't have the vacuum, and we permanently have some quantum fields.
Okay.
For instance, yes, and can we solve and get such black holes with the quantum fields in the right hand of the Einstein equation?
So I should probably answer immediately. That's actually my work. The work I'm doing is trying to understand how quantum fields affect on the gravitational backgrounds and vice versa. So I am really happy to answer this question, but probably we should postpone this discussion because it's, let's keep task small. Because, yeah, the Einstein equations look like this. Okay, let me answer. Einstein equation, that won't take long. Einstein equation looks like this, but here on the right-hand side, in case of if you have quantum fields and matter, if you have classical matter, you have like this. If you have quantum field with some coefficient with Newton's constant here, it's actually for probably 8 pi g, yeah. Plus actually 8 pg with quantum average of something. Actually, you can include these guys into this. It's a matter of, in case if you can neglect this guy, so approximately 0, then everything is perfect. In case if you can't, you have to take into account back reaction. But that depends on many things. For example, in what state, because here you average with respect to some state, not even necessarily pure state. It can be trace over the density matrix, etc., etc. So, and everything depends on quantum fields and state they are staying in. And I mean, in case if the quantum fields, well, there are situations when this guy can be neglected.
So I have a question, maybe on the general stuff. You solve the equation r mu equals to 0, and still you have a mass somewhere.
Yeah.
So,
but mass due to gravitation. Gravitational field can also carry energy. In that sense, I have energy or mass, if you wish.
No, I think that Rg is defined full mass.
No, it's just a scale. It's just a, you see, this metric describes gravitational field of any spherical body beyond its position. So for example, spherical star will have this gravitational field, which spherical star that doesn't rotate will have this gravitational field outside of it. Inside, you will have a different metric. There is so-called inner solution, which mimics metric of the star. But the black hole is the situation when there is no surface, there is no body of the star. So it's just a scale present in the solution. Nevertheless, there is no body. So there is no place. So there is a singularity and deviation of the metric from flat one at infinity.
Yeah, I think I have just maybe a question of the mathematical ground. So we should have T minu.
Should is two. In general, we have.
In general, if we have a mass somewhere, I would assume that it should be there. But probably just in a single point r equals to 0.
Okay, okay.
So my question, why we don't use Dirac delta function?
No, it doesn't have, it is actually, it is not a solution with delta. From the mathematical side, this solution is not a solution with delta function on the right-hand side. There is no delta function on the right-hand side. So yeah. It's not the same as, for example, this guy. Up to a coefficient here. It's not the same. You see? Yeah. It doesn't follow from the same. So we don't have delta function on the right-hand side. We have a singularity, but we don't have delta function on the right-hand side. It's more complicated. Delta.
I think that Schwarzschild, first when he realized this solution,
yeah.
The delta function was not yet invented.
No. The delta function was invented long before. You mean Dirac didn't invent it, but Gauss and Heaviside invented it long before Dirac. Well, probably Schwarzschild didn't know, I cannot exclude. Yeah. But in any case, there is no delta function on the right-hand side.